Hello, Dave Kenworthy here. It's 12:28 on the 12th of the 6th, 2021. And yesterday I said that I'd look at the Giza model today, but I've changed my mind. Because I've been looking at a video by Professors Wildberger and Mansfield. Obviously about Plimpton 322, but more than that, it's about the Babylonian calculation for root 2. So we can go and have a look at what they're saying. These guys are absolutely brilliant. Now, I've watched all these videos over and over again, so I know what's in a lot of them. And I've learnt so much from watching these videos, and I'm sure I'll learn a lot more as we go on. But I mean, let's just talk about these two professors are obviously worked together on this project, and they've translated Plimpton 322. And this picture here that's coming up of Professor Mansfield holding Plimpton 322, wearing a pair of gloves, white gloves, looking very, very pleased that he's holding the tablet. I mean, that sends such a great message out that these two professors are really breaking into something quite new here with all this research. And I'm happy to go along with everything that they're telling us. And hopefully I can follow up on some of their advice. So we're going to go into this one. Let's go back again. YBC 7289. And it's about root 2 and the line across the central diagonal is the Babylonian estimation of root 2. And it's 1.24.51.10, and that's it. The .07 and 046 have been put in by the professors, not by the Babylonians. So let's have a look what they're telling us. Let's just drop into anywhere. They're telling us how the Sumerian wedges were used to produce the figures. So we need to understand this first before we can start understanding the way they notate their numbers. So it's 13.37.10. Completely different from the way we do it, really. So let's move on, because we can find where we get to this tablet, this root 2 tablet. Here it is. So they're just finishing off talking about Babylonian triples, that's Pythagorean triangles.
Alright, now let's have a look at YBC 7289, which is a very famous tablet, which illustrates more of the power of old Babylonian mathematics and their sexagesimal system. And also the fact that they were not afraid of dealing with things which were approximate. So this is a geometrical diagram that basically illustrates that they had an understanding of the square root of 2, or at least approximately the square root of 2. And it's, you see a square here, and there's some diagonals, and then there's a number over here, and then there's two sexagesimal numbers written over here. And we now have enough experience to be able to interpret what these things are.
Right, we'll move on now towards the end.
But this is a very famous example, but there were loads of perhaps some more gems like this one. Fascinating.
Let's just go back.
And now you know everything you need to know to translate a mathematical tablet from this era. You know the numbers, you know the kinds of arithmetic they did. You can get the old Babylonian table out of the closet and brush it off and read what's on it. Or if you go to a museum, you can look at the Babylonian collection.
So brilliant. And that's exactly what I'm going to do. Professor Mansfield are telling us that now that they've taught us how to interpret these tablets, all we have to do is have a go ourselves, and that's exactly what I'm going to do. And thanks to the professors, because they're doing something astounding, really. Now then, this is a bit of a mess, but last night I watched their video, and I started messing about with this root 2. It's going to be pretty difficult to explain what's going on here because this is just rough workings, but I wanted to go through them because I think they're so important to help us understand this tablet and what these people were doing. Because when the professors are doing their presentations, they get confused themselves about how this system's working. They make mistakes like the side of the square's 30, but it can also be 30 over 60, so it's a half. And at times, the system is so flexible that it's very confusing, and to know what these people were actually doing is not easy at all. And it's taken us further from the systems we use. It's something quite phenomenal, this system, and the more we look at it, the more we find what they were doing and why they were doing it. And what I've got here is root 2. You'd never believe that, but 1, 24, 51 and 10 is root 2 approximate. And why is it root 2 approximate? Because here we can say that these are seconds, and then we can cross-cast and see what these numbers represent in seconds. But we're not dealing with time, really, are we? We're dealing with root 2. But are we? Are we dealing with root 2, or are we dealing with something else? Or are we dealing with both things at the same time? Are we dealing with time? Are we dealing with astronomical observation? Are we dealing with root 2? Are we dealing with a day in time? Are we dealing with something more than a day in time? All these ideas are encapsulated in this one little part of the spreadsheet here. So if they're seconds and that's time, that's a day. 1 day in time. So what's that? 2.5 days. And immediately we think of Thom, because at the root of his system, the root of his measure is the number 2.5. 2.5 has to be in the perimeters of the circles. This is something absolute. This is something that Thom stated over and over again. And 2.5 can be found in this little table here, because the 10 is factored by a 1, so that's 10 seconds. The 51 is factored by 60, so that's minutes. The 24 is factored by 60 times 60, giving us a day. And the 1 is factored by 216000, and we all know about this number from the previous presentation. So that brings something else in. Is this the circumference of the Earth? Because it is in the previous presentation. So we've got a day in time. Why have they got that number there, 3060? Why have they got 51 there? All these questions. How do we work out root 2? That's the divisor. That's the denominator. And this is the numerator. And that's just a sum of all these. So that crosscast, that crosscast, that crosscast, that crosscast comes to that number. We divide it by the denominator, which is 2.5 days. We get root 2 approximate. And it's a good approximation of root 2. And there's so much going on, because if we look at this section of the calculation here, it adds up to 3070. And if we divide 3070 by 86400, we get this number here, 35532. Now, that is very close to a lunar year. And we're looking at really, at Avebury, Thom calculates the lunar year. He doesn't say this. It's my interpretation of his calculation. But he calculates it at this number here. 3542.8, 521 megalithic rods of 6.8 feet, being 1302.5 megalithic yards. And I can show you that because it's here. And we really go for this stuff. Don't know if you can see it. I'll bring it a bit closer so that I can see it. There it is. 1302.5. And he says a lot about this. I'll read it to you. It is seen that all the arcs in the portion where we have definite evidence that the assumptions are correct are close to being multiples of 2.5. A rule which we have seen is almost universal for perimeters. Here we find it applying to the portions of the perimeters between the corners. If the total perimeter was intended to be 1300, the error is only about 1 in 550. But it is unjustifiable to accept this until excavation on the east side has gone far enough to prove the assumed geometry. That's never been done. Thom's work was never followed up by archaeologists. In fact, I go as far as to say that when an archaeologist hears the word Thom, they shudder. The two inner circles have a diameter of 125 megalithic yards, which curiously is exactly 340 foot. Taking pi as 3.14 makes the circumference 392.5, again a multiple of 2.5. This is one of the best rational approximations to pi left us by these people. It was used in the large circle at Broga in Orkney. Note the theme of 25 and 2.5 running through all the Avebury dimensions. The line joining the two inner circles is 145 megalithic yards and lies at an azimuth of about 340.2. So 1302.5, and we can get that out of this tablet. Now this tablet is a square root calculation device, and because I'm using a spreadsheet, I can show you how it works. I can change that number there. It might be 10, it might be 1, we don't know. But if it's 1, the professors tell us this. We're not sure, we don't know. But we do know it could be. So if we put 1 in there, we get this number here. 35428, which is the Avebury perimeter. Just by changing that number, which we're not absolutely 100% sure should be 10, we get that. We get 354.28. What is the chances of that happening? I'm going to change it back because some strange numbers have come up. So let's change it back to what it should be. And that's astronomical. So now we've got the Earth's circumference, we've got time, we've got root 2, we've got the Avebury perimeter, all in this. And what I was looking at last night was, we know that this is their root 2. We know that that's it, because if that is 10, which I'm pretty sure it should be, we've got this 305470 divided by 216000. So that we know is their root 2. And we know the Egyptian root 2s are, one's this, 99/70. So to get that, this figure, if we're going to divide by 216000, has to be 305485.7. And we can subtract the difference between that and that to find this number here, which is 15.71429. Now if we divide that into that, we get 19440, which is incredible. Because now there's definitely a correlation between 99/70 and this version of root 2 here. So if that is giving us 19440. What's this giving us? Dividing by this. So let's just have a look. .19439. So that's a ratio between 99/7 and Babylonian root 2. Now just before we finish, this version of pi, from Berriman's work, we know that this version of pi, from Berriman's work, we know root 2 time divided by 0.45 gives us pi. Divide by 0.45 and we get pi, right? So if we do this one, we get, divided by 0.045, well played, Dave. Right, there we go, 22/7 that is. And it's really difficult going through this because there's dead rough, these workings. What I've also done is I've worked out pi, root 2 as 140/99 up here. That's what that is. That's the second version of Egyptian pi, because I wanted to see if there was a correlation between these two. And the number here is 30545.5, so it's less than that. But we take one from the other and we get this, 15.45. And if we multiply these two together, we get this. And if we multiply that by 7, we get this, 1700, which is Thom. So he's in all this. Thom's numbers are in all this. Now, this is what I did last night, so I need to really pull this together. But I just thought I'd show you the way that I work. This is the way that I analyse these numbers. So if you get two different numbers, subtract one from the other and divide the difference into each one, you can see if there's this Babylonian relationship or Egyptian relationship, which is n divided by n minus 1, or it can be n plus 1 divided by n. It doesn't really matter. I don't like using mathematical notation because I'm not a mathematician. I just like to use numbers. But that is standard Egyptian scale. You always get 176/175, 120/119. You get it all the time in Babylonian and Egyptian calculations. So I have to try and understand why we get it and what it means. And this is the way I do it. But there's a lot come out of this row of root 2 numbers here. If you went to a mathematician and said that's root 2, approximate, he'd just laugh at you because he'd have no idea of what's going on here. But because we've got the professors telling us exactly what's happening, we can go and do exactly what Professor Mansfield said. We can do it for ourselves. And we can show people what we're doing because it might help other people who are doing this as well to apply their approach and see if they can get something that approximates to what I'm finding here. But there's no doubt about this. These people were using root 2 approximates, and they were deliberately calculating them. And we can see here, we that doesn't have to be 10. It can be any number you want it to be. If it's 11, we get root 2 being more than actual root 2. That's actual root 2 there. Well, when I say actual, it's what this program, this Excel program produced when I drag it into that square, into that rectangle. So that now is more than this. But we go back to 10 and it's less. So just that one unit changes root 2 from being less than the actual to more than the actual. So what a powerful tool they've developed here, these people. And there's so much going on. And it's so complex that it's almost scary. So that's all for now. That's just sort of something I wasn't planning to do, but I hope it's helped to explain what I do. Cheers, thank you.